Hi, welcome to one and all. Next, we have the section, the finite Fourier series of the Dirichlet characters. Here, before going to this section, let us recall what we have studied earlier about the properties of Dirichlet character chi mod k, which is periodic mod k. Then we have already studied that Dirichlet character chi mod k is periodic mod k. It has a Fourier series expansion chi m, which is equal to sigma n equal to 1 to k a k of n e raised to 2 pi I mn by k. And we have studied in theorem 8.4 that its coefficient is given by a k of n is equal to 1 by k sigma m equal to 1 to k chi m e raised to minus 2 pi I mn by k. This is what we have studied earlier on the Dirichlet character chi mod k. Now, here you have to note that this part, this is nothing but we all know that what is Dirichlet character chi, what is the Gauss sum g of n chi g of n chi is summation m equal to 1 to k chi m e raised to minus 2 pi I e raised to minus 2 pi I mn by k e raised to not minus e raised to 2 pi I mn by k. So this can be seen as g of minus n chi. So this part can be seen as g of minus n chi. So this a k of n can be rewritten as 1 by k times g of minus n chi. So thus we can have our theorem, that is the finite Fourier expansion of a primitive Dirichlet character chi mod k has the form chi m is equal to tau k of chi by root k sigma n equal to 1 to k chi bar n raised to minus 2 pi I mn by k, where tau k of chi is g of 1 chi by root k equal to 1 by root of k sigma m equal to 1 to k chi m e raised to minus 2 pi I m by k. This is what we have to prove. Also, we have to prove that the number tau k of chi has the absolute value 1. This is what we have to prove. So the proof is quite simple. Because we have already studied many properties of primitive Dirichlet character chi. Since chi is primitive, we have proved that g of n chi is separable. This is what we have proved earlier. So since chi is primitive, g of n chi is separable. So g of n chi is separable means g of n chi can be written as chi bar of n times g of 1 chi. That is what we have studied. So instead of n, if we put minus n chi, then we can write g of minus n chi will be chi bar of minus n g of 1 chi. So and we have already written what is a k of n. It is nothing but 1 by k g of minus n chi. So by using this results, a k of n can be written as instead of writing this, we can write this as g of chi bar of minus n times g of 1 chi by k. Now let us come to what we have to prove. It is we have to prove this value of a k of n. So here we'll be writing it like this: chi of m. What is chi of m? Chi of m is nothing but sigma n equal to 1 to k a k of n e raised to 2 pi I mn by k. By our definition of a k of n, which we have written now, we can replace it. So it will be g of 1 chi by k sigma n equal to 1 to k chi bar of minus n e raised to 2 pi I mn by k. Now here this g of mn by k, g of 1 chi sigma k equal to 1 to k chi bar of n minus n e raised to 2 pi I mn by k can be written as chi bar of n g of 1 chi by k chi bar of n e raised to minus 2 pi I mn by k, because we have taken chi bar of minus n is chi bar of n times e raised to minus 2 pi I mn by k. Now this is nothing but g of 1 chi times uh, this is g of 1 chi times this part we are going to split. G of 1 chi by k is going to be split into 2, that is g of 1 chi by root k times 1 by root k. That is what I have written here. So here it is sigma n equal to 1 to k chi bar of n e raised to minus 2 pi I mn by k. Now this g of 1 chi by root k we are going to give it as tau k of chi. So this is tau k of chi by root k, and the remaining is sigma n equal to 1 to k chi bar of n e raised to minus 2 pi I mn by k. Now this there is a mistake here. Here it is yeah, it's correct, because we have replaced this by minus chi bar. We have taken the complex conjugate, so here it is correct. Now this part we can write it as this part we can write it as tau k of chi is g of 1 chi by root k. This g of 1 chi by definition of Gauss sum is nothing but 1 by root k sigma m equal to 1 to k chi m e raised to 2 pi I m by k, because here n is 1. So 1 by root k sigma m equal to 1 to k chi m e raised to 2 pi I m by k. So by using the theorem which we have studied earlier, we have studied the g of absolute value of g of 1 chi square is k. When chi is separable, we have g of n chi is separable, we have studied that the absolute value of g of 1 chi square is k. So absolute value of g of 1 chi is root of k, and hence this we have to take the absolute value of this. Absolute value of this is g of absolute value of g of 1 chi by absolute value of this is root k itself, so it is root k. So here the absolute value is root k, so root k and root k gets cancelled and you will get 1. So thus we have obtained the result. I hope you have understood the result properly. Now here what we have taken is that here please note that here what we have taken is we have taken the complex conjugate of the same. That is why here this minus n is gone, and that minus n has been replaced here. So that is why this sign change came. Now this completes our this chapter or this module on periodic arithmetic functions and Gauss sums, and we have so far studied many properties of periodic arithmetic functions as well as Gauss sums. I hope you have all understood the concepts clearly, and so far we have studied many results. Please study these results properly, as well as if you have any doubts you can ask me anytime by sending messages, and some previous notes contain some errors which I have rectified in these notes, and I hope you will be taking the printout of this last set of notes which I am going to upload, so that notes is better to be carried for your learning purpose. And further there some clarifications are needed, which I will put in my next lecture session on Dirichlet characters. I will give some brief idea about the and a brief example, some examples of Dirichlet characters also in my next session, and I hope this module is comparatively easy for you to learn. And if you have any doubts, you just send me messages or you can call me anytime. And thank you very much for your patient listening. Thank you.